Okay, this is it's a calculus problem. It's basically a volume of revolution, but from parametric equations. So, as you'll see, we're going to actually form a Cartesian equation and then do the volume of revolution uh, from from that. Okay, so here we've got this question, which incidentally is from an edXL specimen paper, called Pure One paper, um, further maths paper. And we got an image here. Figure 2 shows the image of a gold pendant, just height 2 centimeters. And so this is it's like a teardrop thing. So it could if you spun this around the its chain, if you imagine the chain here, then the profile would appear the same from this or any angle. Um, okay, the pendant is modeled by a solid of revolution of curve C. This curve C has parametric equations that and y equals that, x equals that, y equals that, 0 to 2 pi. And first of all, show that a Cartesian equation of the curve is that. Right, so um, So I've kind of I've sort of drawn this. So it was kind of useful to see how the parameter relates to the Cartesian thing. So I've just taken values of x and y for values of theta naught pi by 2 pi and 3 pi by 2. Obviously 2 pi is going to be the same as for 0 with this particular curve. So that's how it goes. We start off there and we basically work our way around here as theta increases and come around and then back to there for 2 pi. So that is how it's shaped. Right, so how are we going to form our Cartesian thing here? A very simple uh, parametric to Cartesians. You can very often can just um, make both explicit in the parameter and then bang the two together. But in general, what we're really trying to do is do something a little bit more subtle than that. In this case, we're going to rely on the Pythagorean thing. A lot of these trigonometrical ones do the same thing. So when we look at the y equation, we can write it like that, and in particular, we can write it like that: 1 plus sine theta equals minus y. That's what that is. Look at the x equals cos theta. Well, sine 2 theta, that's the double angle formula, isn't it? It's going to sine 2 theta is equal to sine theta, it's 2 sine theta cos theta. So when we then multiply by the half, we're going to get sine theta cos theta, and we can factorize it like that. Which is nice and convenient because obviously then we can do our substitution of 1 plus sine theta in there and we get x equals minus y cos theta. Or what we really want is cos theta equals minus x over y. So now we've got sine theta and cosine theta in terms of x and y. And that is a common theme with these things, to find an expression for sine theta and cos theta. And once we've done that, then we can glue them together by use of the Pythagorean identity. Sine theta squared being that, cosine theta squared being that. And then we got it. That's basically our Cartesian equation. Now we've got to do a little bit of manipulation on it, but that's just going to bring us down to that x squared. Now that is explicit in x squared, which very conveniently is what exactly what we need. Because part B is hence using the model find in cubic centimeters the volume of the pendant. Right. So if now we this is a an integral with respect to d y. So what we're actually doing is we are adding. If you can imagine, this is there's a whole infinite number of disks here that this pendant is made up of. Okay. Um, and the area of each of those disks, because we're spinning around the y-axis, aren't we, is going to be pi r squared, where the radius is this. The radius is the x coordinate. Yeah, pi r squared, and we're going to do that between there, going right down to there. So our integral goes between 0 and -2 in the y direction of pi r squared, where r is the x coordinate here. Right. Right. So that is what we want. So that's the sort of that's the radius squared. That is the represents the kind of infinitesimally small width. Now we can't actually do this because we need to be, if we're dy, we need the function in terms of y, but that's fine because we've got a ready-made conversion here, which we can substitute in there. And then now we're just applying the power rule, aren't we? To that to give us this integral, pi factorized out there. And then when we evaluate that between 0 and -2, well, of course, the 0 don't contribute anything. We're going to get this, which is, in fact, 8/5 multiplied by the pi that we've got in there is going to be 8 pi by 5. All right, so that is your volume of revolution of that, which is the volume of the pendant. Okay, so I think that's kind of quite a nice, interesting problem in actual fact. So yeah, so we've got a volume of revolution, but we've started with a parametric curve, so it's kind of a synoptic question of parametric equations on the volume of revolution. So hopefully that has been useful, and thank you for listening.